humbling honor to be here today and to receive this wonderful acceptance to the Accademia dei Lincei. It's also an honor to tell you about fusion, not to create the elements and power the stars, but to give us energy on Earth. So it's my duty to now literally go down on Earth and tell you what we do. When I say we, I speak, of course, for my own research area where I am based in EPFL in Lausanne, but also for the European consortium that I run myself now, which is called Eurofusion, which encompasses the 29 states, the 26 members of the Union, UK, Switzerland, and Norway. And the picture here is representing these two geographical elements and also the element that we actually, in modesty, trying to do, that is to bring down to Earth the fire of the stars like Prometheus. We had great introductions in the morning and just a few minutes ago about how the stars work, so I don't need to repeat that. I just remind you that if you move around the axis of all possible elements that we have, and in terms of the mass or energy per nucleon that you have in a nucleus, you can gain energy by splitting the big nuclei, and that is nuclear fission. Of course, that's what already works for producing energy in the plants. Or you can do the other way around, and that is to put together very light elements. In the case of the sun and the stars, you start from the protons. In our case, we need to be a little bit smarter than the sun itself because we don't have as much time, and the sun and the stars do. And so we will use slightly different nuclear reactions, but the principle is the same. Basically, eventually, you put together protons to form helium. And this curve is also nice because visually represents the fact that if you do that, as opposed to breaking big nuclei, you go down much more steeply in this curve, which means per unit mass, you actually gain even more energy than you do by doing nuclear fission. So this density of energy, number of megajoule you can extract per kilo, is the largest of all that you can have in nuclear fusion, of all possibilities we have on Earth. So I would say we have to be smarter than the sun and the stars. We cannot do the PP proton-proton reaction. It's too slow and too low probability, too low cross-section. So we have a few options. And because it's difficult enough, let's choose the easiest of all, which is the deuterium and tritium option. So these are two isotopes of hydrogen. Deuterium we have plentiful. It's an element that is everywhere, in water, for example. Tritium is a slightly different story, which I mentioned a few words about in a moment. This reaction leads to helium and a neutron, and of course, a lot of energy. Now, in order for that to occur, because the nuclei are, of course, positively charged, and they repel each other, you need to make them smash against each other, a very high energy, which means in a disordered way, very high temperature. And very high temperature means tens of keV or hundreds of millions of degrees. Even the easiest reaction of all, to have a decent rate, needs hundreds of millions of degrees, and that's the DT reaction. At which temperatures, of course, you don't have anything you know of in usual way, on Earth at least. That is, you don't have solid state, you don't have liquid state, you don't have gas state, you have what we call a plasma. So when we have seen all those beautiful images in the morning and just now, we were actually observing plasmas. And that is a soup of charged particles, or globally neutral, which is moving in all directions, very difficult to control, and in which all the molecules, of course, are dissociated, even all the atoms are dissociated. So you have protons and electrons and nuclei that are free to move. So that's plasma. On Earth is a very exotic state, but the rest of the universe that we know of, we heard is 5%. Most of it is in the form of plasma. So it's not such an exotic state outside our atmosphere. So I say the DT reaction is what we need to use, at least in the first generation of power plants. It has a few interesting features. It has the highest probability of happening, and this is already a very good thing. Second thing is that the fuel itself can actually be reproduced relatively easily, at least in theory. Why? As I said, deuterium, we have it. Tritium is short-lived. It's about 12 and a half years of life. Is unstable, and we don't have more or less any on Earth. We only have tens of kilos. It's a very, very small amount. But the good news is that the neutrons that comes out of the fusion reaction, which has a lot of energy, it will be used to heat the coolant and therefore create heat and therefore electricity, but also can be used to react with lithium, which we will have to put around our little star, and what we call breed tritium, because a neutron plus lithium, and if we use lithium-6, we can do it at a very high probability and also extract even more energy, and that will produce a tritium nucleus, which can then be reinjected in the plant. So tritium is neither coming in from outside nor being ejected to the outside. It's generated in situ, and that's crucial. The other product of the reaction is helium, or the nucleus of helium, which is an alpha particle, which is also part of the plasma, if you like, and which is going to be kept in there to heat the plasma itself and maintain the temperature that we need. So that's the idea. Why do we pursue it so intensely? And more intensely now that we realize we really need the base load electricity source in addition to the renewables, because this energy density that I mentioned before is fantastically large. If you think about the chemical reaction like normal combustion, in terms of megajoule per kilogram, you have of order 20, 25, 30. So tens of that quantity. You go fusion, you have 350 millions. So 25 as opposed to 350 millions, which means the fuel is practically inexhaustible if we make it work, and it's also very well distributed geographically, because essentially you take it out from water, which is better distributed than oil. We have no greenhouse gas emission, obviously, and no long-lived radioactive waste. The reaction itself doesn't produce any waste. Of course, the neutrons, that energy can activate the metals that are around the machine, but that's local, and that's not such a long-lived activation. And we don't risk of losing control because our concept is not based on chain reaction. Neither do we have a large amount of fuel at any given time in the plant, only a few grams, because of this fantastically large energy density. And in the approach that I'm advocating today, and the one we follow in Europe, the magnetically confined approach I say a few words about, we are not linked to any weapons program in the world. Obviously, it's a concentrated energy, and it's not subject to the intermittency that renewables are subject to. So it is difficult to do it because the plasma wants to go everywhere. It's very hot, very difficult to contain on Earth. You have to hold it together. And you have to hold its energy together for long enough for it to give it back to us with a nice gain. The stars have an easy job because they are big, so they can keep the plasma together by gravitation. Of course, that is not viable on Earth. And we have two other possibilities. One is basically to do mini implosions on what we call pellets, so kind of little pills of fuel that you may implode and then explode, for example, by injecting a very large number of lasers on their surfaces, either directly or indirectly through a bath or X-rays. This is what we call inertial fusion, and there's, of course, also stimulated in the research by the fact that it simulates thermonuclear explosion. So this is an interesting approach for the extreme science and physics conditions, but it's also an approach that is not so free from relations and links with the weapons programs. Now, in that case, you have a lot of power, a lot of pressure, a lot of density, a lot of plasma, and you can afford having it only for a very small amount of time, because the product of the two is what it counts, how much plasma you hold there and for how long. The other approach is the one that we're taking, is based on the idea that the plasma is made of charged particles, so the charged particles are trapped in a magnetic cage. You have to just make a very clever cage to trap them long enough. And in that case, you can trap for macroscopic times of order seconds, and the energy can stay for the seconds. Therefore, you don't need much of a density. The density we need is 10 to the 20, which is 100,000 less dense than the air we breathe. And this is what we do in our program. Now, to hold the particles together, you need to have a cage which is optimized because of the particle motion that goes all over the place, and it's fairly complicated. So you need to have a helical system, and it's closing on itself. So it's that sort of donut shape or torus, but with helical field lines. You have two ways to do it. One is a clever way that was discovered in Russia called the tokamak, in which you combine the fields that you generate with magnets from outside with the field that's generated by the current that flows in the plasma itself. And that works very, very well. In fact, that's where we have the highest parameters of the plasma on Earth that we can achieve. And the product of the density times how long we hold plasma energy for times the temperature that we hold it at is by far the best we have obtained ever. Trouble is, in this case, you have to make the plasma current by inductive action, which is intrinsically non-continuous. And if you all of a sudden lose the plasma current, you don't have an accident that puts safety in concern for human beings, but you have a little bit of a problem in your machine. So the other option that we are also pursuing is the one in which this complicated helical-like shape of the cage that we create is actually made by coils that themselves have a very complicated story, very complicated geometry, which is nice to design on a computer, but it's much more difficult to produce at the industrial level at the scale that we need for a plant. And this is also a promising avenue, although so far it has the value of the performance, if you like, parameter about 60 or 70 times lower than the one on the tokamak. Now, a couple of ideas why is this difficult, also from sort of a physics point of view. You have a system in which you have turbulence. You have seen a beautiful talk about Boltzmann equation and so on. This is a system which is turbulent, but it's electromagnetic turbulence also, in addition to fluid turbulence, because the plasma particles and pieces of fluid are at the same time sources of electromagnetic fields and victims of electromagnetic fields. So it's a very intrinsically nonlinear system, and there are a lot of collective effects. We have to deal with very small orbits of the particles. At the same time, we are building a cathedral-like machine. So we have many, many scales that coupled, and many scales that we need to cover in space and time, for example, if we want to simulate what happens in there. It's a system that actually is not a physics experiment eventually, but it's a reactor that produces electricity, has an intrinsic complexity and also an intrinsic three-dimensional character. As I said, it's very turbulent. You can imagine the gradients that you have in there. You have something that's much hotter than the center of the sun at the core of this device. And then at the edge, which is a couple of meters away, you have coils that are superconducting almost at absolute zero. So you can imagine the incredible gradients that you have there of temperature or pressure, which of course are thermodynamic potential that drive instabilities. And it's a system that's multi-physics in the sense that you have the core of the plasma is this star which is very hot, so it's totally ionized. You don't have molecules, you don't have even atoms, you don't have collisions, but the edge of our plasma has, of course, a bottle which is made of material, and then so you have a transition from pure, completely ionized, completely hot, non-collisional plasma in the core to atomic physics, to material physics, to impurities, to completely non-thermal behavior. So our system is very rarely at thermodynamic equilibrium, and so on and so forth. So you have a multi-physics environment. And to visualize that, I have this movie, which is actually made with actual particle trajectories that we simulate in a field of a tokamak, where you have, again, populations that are known in thermal equilibrium with each other, where you have instability, sort of bubbles, like solar eruptions at the surface of the sun, which are beautifully observed on the sun. For us, they are a complete disaster, because that means that you have an eruption of plasma that's thrown out all of a sudden to our material surfaces, to our bottle, if you like, which is why our bottle is actually made of very special materials. As of today, we know how to manage that, but we need to manage that in a power plant, which means we need to manage tens of megawatt per square meter, not for a few seconds, but for 24 hours a day, 7 days a week, 365 days a year, and maybe for a few decades in order to produce electricity. So this is sort of a complexity of our endeavor. And the key word for me, for fusion, is integration. We need to understand all these building blocks, and now we do, most of them. but we need to put them together. They need to work together. They need to work together in a system which is, we call it a system of systems, which is not only a little star in the center, which is, in a sense, almost the easiest part, but it has to be, kept stable. It has to be fed with the proper fuel. It has to be pumped because the fuel that you don't need anymore has to be sucked out. So you have to have an almost perfect confinement, but not quite perfect because you want to suck out something because that is what you don't need anymore. Then you have walls, which you want to withstand heat loads that are comparable to when you launch a rocket. Then you have coils that are almost absolute zero, which produces the highest fields you can think of, many Teslas, and then you have to have a system that extracts the power and refuels the system, the plant with tritium that we produce in that mantle around which we call the blanket. So it's a fairly integrated thing. You may think, oh, this is impossible. No, we are about to get there. About to doesn't mean tomorrow, like some people promised. In my opinion, means a couple of decades. But why are we certain that we're going to get there? Because we have obtained many important results. I cite two of them. Of course, the two records. One is on the right here. Is 1
minute.
1 minute, okay.
Or maybe two.
Maybe two, okay. So this is a result obtained with a pill that's imploded. The pill was producing more energy than was used to make it implode, but not more energy than was used to generate the laser beams with which that was imploded. Okay? And the one on the left is the one we obtained in Europe, in the tokamak in United Kingdom, run by our consortium, in which we produced the world record of energy, 69 megajoule, using 0.2 milligrams of DT, as opposed to a few kilos of carbon, if you like, for the same amount of energy. Now, we're putting together the integrated proof that this can be done in ITER. This is a worldwide experiment being built in the south of France that will demonstrate that we can gain power out of the plasma. So plasma will produce more power than we inject for the first time. This is an international treaty. It's maybe the most complicated thing we ever done together. And it's about to start operation in a couple of years. It's, of course, a difficult exercise to put all the things together. But that's not the end of the story, because the end of the story is when we demonstrate that we can do it also not only as a scientific experiment, but also as a possible commercial reactor, which means our star has to be there producing energy for, as I said before, a long time, and also at an economical possible level of the cost of electricity. So in order to do that, we have the step that we consider necessary. We call it demo in Europe, which means we produce 300 megawatts, few hundred megawatts electrical power, which means about a gigawatt thermal power for a few hours at a given time. And then we do that repetitively throughout the day, throughout the weeks, and so on and so forth. And for that, we need still to address a few gaps in our knowledge, in physics and in technology, and especially, as I said before, to put them together. So we need all of that in one system, and for that we also need fully international collaboration. Thank you very much.
Thank you very much, dear colleague, and your stay there because we have time for the questions you have been listening to.
I have two questions. The first one, as far as I could understand, the fuel that you use is lithium and deuterium, because tritium generates itself with the efficiency 100%. So the tritium is regenerated itself in the overall thing.
Absolutely, you understood perfectly correctly.
Second question, you say at a certain point that it is more convenient to have an helical but why? So in the comparison between the tokamak and the stellarator will work well, better than the tokamak. But you show that in Japan they're getting better results than in Germany, or not?
Yeah, the stellarator potentially are interesting because they're not subject to what we call disruptions. If you lose the current in the tokamak, all of a sudden your cage is no longer the one that is supposed to be to hold the particles together. And that is something you absolutely want to avoid. But when you don't have that, the tokamak performs much better. holds the plasma better together, holds these non-thermal components of the plasma better together. The stellarator has the potential to be very good, but it hasn't shown yet the degree of confinement that we have shown in the tokamak. I say we because in Europe we have pushed for the tokamak. Yes, so the stellarator still has to be proven to be able to reach the level of performance that the tokamak has reached. So jury is still out on what will be eventually the power plant. Maybe they will be different. There will be one stellarator. Thank you.
Other questions? Down there.
Yes, a very nice talk. Thank you. We just had a few weeks ago a meeting here. The Academy just devoted to fusion, nuclear fusion. Of course, there is a lot of connection with basic science, the disruptions that you are very fearful about are loved, of course, by astrophysicists because you accelerate particles.
Yes.
There, so there is a very strong connection with cosmic and space physics, astrophysics, and fusion. So my question is, you think that big projects like ITER or similar that also are for the near future can find a good way of dealing the basic research done also by smaller experiments? So you think that in some way you can support at the same time big experiments, but also a number of smaller experiments, also by private companies, also by public institutions, just because the science is still very important. There are lots of questions unresolved.
My answer is absolutely yes. It's not a very academic field, but I have the chance of being in academia. When I was at MIT, I built an experiment to study what's called magnetic reconnection, which is the change in topology of magnetic field, which happens in the geomagnetic field, in geomagnetic tail. One of the mysteries is how fast it happens. It should not be happening so fast. So we in the lab have studied how you can justify that it happens so fast. The solar wind shouldn't come so efficiently inside our atmosphere, but it does. And why is it? Why do I mention this? Because it's a very small academic experiment, or relatively small. At the same time, it explains or can address some of the concerns we have in the large, gigantic tokamak. Because in there, you also have the breaking and reconnecting of the field lines because of some instability. So, and one thing informs the other. So I absolutely agree with you, I think that's what you imply with your question, that we need both. We need all hands on deck. We need basic physics. We need to understand the basic phenomena. We need to understand the technology elements, and most importantly, we need to bring all of these things together. Our field is not as modular, for example, as high energy, where you have an accelerator and then you see several experiments. Our experiment is actually putting it together and running it together because everything is coupled. All the scales are coupled. So we need to understand the building blocks, but eventually the only demonstration that will be convincing is when we'll have the building blocks all demonstrated together. But in order to do that, we need to absolutely, as you say, address the building blocks. And still some of them need to be addressed. Many of them we have, but some of them are still there to be addressed.